Welcome to this puzzle session. Here is the problem we are looking at. So it's given that a man eats at least one apple a day, and suppose in 30 days, meaning in a month, he eats a total of 45 apples. We want to show that he eats exactly 14 apples in some sequence of consecutive days. So I hope the statement is clear, and it's quite interesting that it's not just some kind of bound that at least this much or at most that much. It's an exact number that we can say that okay, this much he must consume in some sequence of consecutive days. All right. So I'll be discussing two solutions of it. The first one is a very slick solution, and then the second one, well, you decide. So suppose these are the numbers of apples that the man eats in the first 30 days, meaning in the total of 30 days. So on first day he eats A1 apples, second day he eats A2 apples, third day A3 apples, and so on. And define bk equals, which is of course another way to write A1 plus dot 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 ak. So this is bk. So what is bk actually recording? Bk is recording the total number of apples consumed up until the kth day. All right. So here is the goal of the problem. The problem can be recasted in the following way. So what is being asked is the following. To show that there exist I less than j such that bj minus bi is exactly 14. So this would mean that starting on day I plus 1 up until the jth day, the total number of apples consumed would be exactly 14 if we can show that. All right, so here is the key idea. So consider the numbers. B1, B2 up to B30 and B1 plus 14, B2 plus 14 up to B30 plus 14. So these are a total of 60 numbers. And they range between, each of these numbers is in this range 1, 2 up to. He consumes a total of 45 apples in the given 30 days. So B30 is 45. I should write it here. So B30 equals 45. And obviously these are in increasing order. B1 is less than equal to B2 is not less than equal to, in fact, strictly less than B2 because he's consuming at least one apple every day. So let me mention that here. It was given in the problem that this is the case. AI is at least one for each I. So yeah, so B1 is less than B2 is less than B3 and so on. So that's the kind of ordering here. And similarly, B1 plus 14 is strictly less than B2 plus 14 and so on. And since B30 is exactly 45, this is 45. This number is 59. And therefore, each of these numbers is in this range. No number is outside this range. And these are 60 different, not different, but there are 60 numbers. So 2 of them must be the same. Right? 60 numbers within this range, 2 of them must be equal. This is the pigeonhole principle or common sense. So thus, there exists I and j in this range of indices such that, well, all right. So before I mention that, 2 of these numbers are equal, but note that no 2 of these numbers are equal. They are in strictly increasing order. And no 2 of these numbers are equal. They are also in strictly increasing order. So there is a number here which is equal to a number there. So this is what I'm going to write. So there exists I and j such that bi, or let me not write bi, let me write bj equals bi plus 14. So there is a j such that bj is equal to bi plus 14. Right, that's what we just argued, and this finishes the proof. This implies bj minus bi equals 14, and it is automatic that j is greater than I because b1, b2, b3, they are in a strictly increasing order, so it is automatic that j is greater than I. Okay, so that's a very nice, very short solution to a fairly puzzling problem. And this is not how I thought of it. I thought of a different solution, and which is what I'm going to present now. So again, the notation remains the same. A1 up to A30 are the number of apples eaten in the 30 days. And again, bk is the number of apples consumed up until the kth day. And here is a simple fact. Forget about the problem. Suppose we have some positive integer and a sequence of n plus 1 integers. Then there exist two different indices such that the difference of the bi's and bj's, what am I saying? Such that the difference of the corresponding, bi's is divisible by n. So it's like this. If you have three numbers, b1, b2, b3, some two of them will have the property that they have the same parity, meaning either both are odd or both are even. Right? That's pigeonhole principle, and that is what is being used here. To actually prove this, you just consider the remainders modulo n. Record the remainder of this modulo n, remainder of that, remainder of that. So there are n plus 1 numbers in this range, 0 up to n minus 1. This is a set of size n, while you have n plus 1 numbers ranging in the set. So two of them must be equal. If two numbers leave the same remainder modulo n, their difference is divisible by n. So that's how one can prove this. Fairly intuitively obvious fact. Okay, so now we have this 30-day. So this is day 1. This is day 15. This is day 15. And then we have the second part. So this is day 16. And this is day 30. So we have split the entire 30-day period into two parts. So here we have b1, b2 up to b15. And therefore, by this orange thing, there must exist two different indices such that the difference between the bi's and bj's is divisible by 14. Right? There are 15 numbers, b1 up to b15. So two of them, the difference of some two of them should be divisible by 14. That's what this is saying. So what that means is that there is some sequence of consecutive days here such that the person consumes a total of either 14 or 28 or 42 and so on number of apples, because it cannot be 0. The number of apples that he consumes in this consecutive period is divisible by 14, but it cannot be 0 because he's consuming at least one apple every day. So it is at least 14, or it is going to be 28, or it is going to be 42, all the multiples of 14. And by the same reasoning, the person is going to consume some number of apples divisible by 14 in this next 15-day period, either 14 or 28 or 42 apples. All right. Now, if this number was 14, meaning the number of apples consumed in this yellow period was 14, then we are done. Or in the green period was 14, then also we are done. So we may assume by way of contradiction that this number is not 14 and that number is not 14. So let me erase that basically. So then he's consuming at least 28 apples here and at least 28 apples here. But then he's consuming at least 56 apples. 28 plus 28 is 56. That already exceeds 45. He consumes exactly 45 apples in this 30-day period. So that's it. That finishes, that's a contradiction to our assumption that this is not 14 and that is not 14. Therefore, at least one must be 14 and that's it. So I think with this analysis, you can prove even stronger results than what the problem asks you to prove. But that I leave to you. So, all right, as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening and I'll see you next time.